Hi there. In this video, we're going to look at making the connections between graph of f and f prime, or the derivative. So this is the graph of our function right here, and we want to graph the derivative. So we need to look at the slope of the tangent line. So for the first one right here, I'm going to just kind of randomly just sketch a slope of a tangent line. It's going to kind of go like this. So I'd say this is up 1, 2, 3, 4 over 1. So this is giving me a slope of 4 at A. So that means at 4, I need to have a point right there. Okay. When I go up to B, it's not quite as steep. Now I always like to start with where my y-intercepts are, so I'm going to freeze for a second and I'm going to switch over and I'm going to go, okay, I'm going to find where I have a slope of 0, because I have a slope of 0 here and here. And slopes of 0, that's where your graph's going to cross the x-axis, because over here is where my derivative is. So at 2, my derivative, or my slope of my tangent line, is 0. So that's going to give me a point here. So now I can start to see, okay, this graph's going to connect from here down to there. Now I'm also going to have a horizontal tangent at 6. So that means it crosses the x-axis here. So right now I have 3 points for my function. I have this point right here, and I have this point here. And so now I want to go think about what's happening to my tangent lines in here. So if I look at the slope of this tangent line, it's still positive. So it's going to be up above the x-axis. It's positive, but it's getting less and less. So that's going to make the graph go down. It's going to get less and less, and eventually it's going to turn to a slope of 0. Okay. Now in this section of the graph, this whole section is giving me a negative derivative in here. So I've got a negative slope, and it's the steepest right in here. So it's all going to be negative, so it's going to be down below the x-axis, steepest in the middle, so steepest kind of right in here. So it's going to come down, and then it's going to sweep back up, because in here it gets less steep, and eventually it's going to come back down to 0 again. And then this section of the graph has a positive derivative, so it keeps going. Okay, now we're going to look at a problem that goes the other direction. I'm going to be given the derivative, and I want to come up with a function. So to do that, first I need to graph the derivative so I can see what's going on. So this is at x is less than 2. I'm going to have a horizontal line that it's equal to 2. Okay, and at x is greater, that was at 2, that I just did it at 0, my bad. So at 2, that's a closed circle there. And then at 2, it's down at -1, so it's going to go this way. Okay. So basically it's saying I don't have a derivative at 2. It's not in the domain of this function, so there is no derivative at 2. Okay. So I go over here, and I know this is a continuous function. So that means I have no holes, no breaks. All right, it also tells me that the graph starts at f at 0 equals 1. So that gives me a starting point for this graph. Okay, so now if I have until x is less than 2, I'm going to follow a slope of 2. So the line's going to be up 2 over 1. I'm going to have a slope of 2. And the graph's going to go up here, a slope of 2. Okay, now even though it says that we don't have a derivative at 2, it says it's continuous. So I need to have a continuous function, so I'm not going to put any holes into this graph. Now I need to have a slope of -1. So if I have a slope of -1, I'm going to go down 1, right 1, down 1, right 1, down 1, right 1, and eventually it's going to come down to here. I'm going to have a graph that's going to go something like that. Okay. And this graph would then continue here because it doesn't just stop at this point. So that is the graph of my function. It's continuous, has a point at 0, 1. The derivative for x in less than 2 has a slope of 2, but the derivative after 2 is -1. Okay. And last, we can talk about one-sided derivatives the same way we talked about limits. So basically, a function is differentiable if the limits from the right and the left hand are equal to each other. So we need these two limits to come out to be equal to each other. Okay, so I'm going to put a big equal sign here. These need to be equal. The right-hand limit and the left-hand limit needs to be equal in order for it to be differentiable on an interval. So let's look at an example. If we were to graph x squared for x is less than or equal to 0, so that's going to be here like this and 2, 4. So we've got a quadratic that comes down here. And then for x is greater than 0, I'm going to do a slope of up 2 over 1, up 2 over 1. And so I'm going to have linear graph there. Okay, so I want to know if it's differentiable at 0. I know it's differentiable at all these other points, but at 0, I need the limit from the left to be the same as the limit from the right. Well, let's look at what it was going to be from the left. If I look at the limit from the left, I'm going to use the function 0 from the right is going to be the 2x. So I'm going to plug 0 plus h in, minus f at 0 over h. I'm going to plug, so I'm basically just plugging 0 into 2, or h into 2x. So that gives me 2h minus 0 over h. So I'm not surprised to find out this slope is 2, so from the right it's 2. Now, if we look at the graph from the left, we're going to say, we're going to use x squared. So it's going to be 0 plus h minus f at 0 over h. So that's h squared, which results in h squared over h, which results in the limit of h. When you substitute, you get 0. So therefore, we can draw the conclusion that this graph is not differentiable at h at x equals 0 because the left hand and the right hand limits are different.